unplug a device, expecting hours of instant, untethered power. But what looks like a simple metallic brick is actually a container for the exact flow of ions at the atomic level. In 1799, Alessandro Volta discovered that a continuous electrical charge could be generated by stacking disks of zinc and copper, separated by cardboard soaked in salt water. Modern lithium-ion technology takes that principle and scales it to extreme energy densities. We pack highly reactive metals into tight spaces to achieve the output needed for global mobility, but that power comes at the cost of high volatility. The system operates on a rocking chair mechanism. Lithium ions are insertable into the layers of host materials, moving back and forth between a negative graphite anode and a positive metal oxide cathode. During discharge, ions move to the cathode while electrons flow through an external circuit, providing power. During charging, those ions are inserted back into the anode, a process called lithiation, to restore the battery's energy. The core engineering threat is that these opposing electrodes naturally want to bypass the external circuit. If they touch, they short-circuit internally, releasing all stored energy in a sudden thermal breakdown. The industrial challenge isn't just generating that spark, but mass-producing a physical system that can contain this atomic chaos over thousands of cycles. This containment starts in the gigafactory, a zero-tolerance environment entirely dedicated to conquering atmospheric moisture and ensuring absolute chemical purity. Inside massive industrial mixers, raw powders like nickel, manganese, and cobalt are folded into polymer binders to create highly precise electrochemical slurries. These slurries are coated onto metal foils and fed through calendering machines, where massive steel rollers crush the foil under tons of pressure. This compression carefully tunes the foil's porous structure. Packing the particles tighter increases energy density, while ensuring the surface is uniform enough to prevent the formation of dendrites, microscopic metal spikes that cause internal shorts. To prevent the electrodes from touching, a separator membrane thinner than a red blood cell is fed between the layers. This porous plastic allows lithium ions to swim through, while acting as a rigid physical barrier to electrons. In a fraction of a second, high-speed mandrels wind the anode, cathode, and separator into a tight spiral. A custom tensioning system aligns these layers in milliseconds, as even a fraction of a millimeter off alignment creates a fire hazard. The core is dropped into a steel cylinder, injected with a volatile electrolyte via a microscopic needle, and instantly laser welded shut to create a hermetic seal. Finished cells enter a testing gauntlet called formation cycling. They are subjected to intense voltage spikes and rapid charge-discharge loads to awaken the chemistry and detect any microscopic internal flaws. Through this industrial gauntlet, raw, unstable chemistry is permanently sealed within a pressurized, rigid enclosure, designed to resist the volatile forces within. While a single cell is a triumph of precision, powering an electric vehicle requires thousands of them. These individual units are networked together and integrated directly into the car's chassis. Governing this massive distributed chemical fleet requires a dedicated digital brain, the Battery Management System, or BMS. The BMS architecture can be centralized or distributed. Module management units continuously monitor the voltage and temperature of individual cell groups. This data flows to the pack management unit, which aggregates information, calculating the state of charge for everything from e-scooters to heavy trucks. Because manufacturing tolerances and aging cause cells to drift apart over time, the BMS performs active balancing. It identifies stronger cells and transfers their energy to weaker ones, ensuring uniform performance across the entire pack. The BMS also acts as a safety shield. If any parameter exceeds safe limits, the system triggers high-voltage relays to physically isolate the battery pack, preventing further stress or potential thermal runaway. This intelligence transforms the battery from a passive chemical container into an active, self-regulating network capable of protecting itself in real time. This engineering makes high-load industrial applications possible, from heavy construction machines to the massive robotic arms in automated factories. Advanced battery tech provides the high power density these systems require. Eventually, the internal chemistry degrades. When an electric vehicle battery drops below 80% capacity, it can no longer provide the rapid discharge needed for highway speeds. But those packs aren't discarded.
Instead, they are networked together to form virtual power plants, where they store renewable energy and stabilize municipal grids as stationary backup supplies. When the cells finally die, global mandates like the EU's WE directive require that the resource loop be closed through intensive recycling. The terminal stage involves complex physical and chemical treatments. Technicians dismantle the heavy housings, so the system can safely extract rare elements like cobalt and lithium from the dead cell cores. Highly efficient recycling processes allow these recovered materials to be fed back into the start of the manufacturing line, reducing the environmental impact of mining and manufacturing brand new components. The modern battery has evolved into a closed-loop system, one that captures energy at the atomic level, powers global infrastructure, and returns its raw materials to the production line to power the next generation.